Okay, so last time I left you with kind of a tense.
Whoa.
Are there solutions to these equations? Are there integers x and y balanced equation? But anybody figure this out? Let's suppose, just for the sake of argument,
Well, I'm trying to do basically try to use like linear equations,
well, these equations are linear.
As long as the x and y are moving linear, like x squared, y squared, yeah, plus and minus,
No, they're not linear because you're squaring x and y.
Yeah.
So let's suppose that you have a solution to this right here, called AB. So let's just suppose for the sake of argument that you have such a solution. And notice there's infinitely many things to check, right? I mean, because this can get very big, then you subtract off 10 times the square, who knows what's going on, right? Well, consider the homomorphism. This is what I'm doing essentially is modular arithmetic, which depending on your background, you may already have some familiarity with. But really what this is this is doing following homomorphism. By the way, I picked 5 here. Anybody know why I picked, given this problem here, why I picked 5? Because 5 is a non-trivial way to make our life easy. And I'll see what. This is a homomorphism of rings, and it's on to. So what does this do for us? This is a squared minus 10b squared, or whatever. But because this is a ring homomorphism, this is a bar squared minus 10 equals squared. And this should be 2 bar, right? Under this assumption here. Right, because if this is 2, then B of 2 is 2 bar. Now this, the A bars, B bar, 2 bar, they're all in C mod 5. What happens when we take 10 times anything C mod 5? This is 0, right? Because in fact, the ring here is characteristic 5. In fact, it's a field. So this thing is 0 bar. And so what I get is 8 bar squared is equal to 2 bar. Everybody agree with that?
Yep.
Now let me make just a little table. And I dig this table because it's fine, it's short.
Zero, that's have 0 probably be the same. 1 bar to the 1 bar square.
That column on the right, squares, in C mod 5. Is 2 one of them?
Yep.
Because 2 bar is not a square in C5. And so we must conclude because if this could ever be 2, that would mean that 2 bar would have to be a square mod 5, which is awesome. So what we've done here is we've taken this homomorphism of rings and we've taken a big problem, that is finding a solution to this that has infinite many possibilities, and reduced it to a small one, right? Where we were easily able to toss it out, right? Any questions? So this is kind of a nice application, if you will. My next one's kind of just to sort of tease you a little bit and maybe get you interested in thinking about the number theory. What about this? Now, before we start, I think we can all agree that if I let x be plus or minus 1 divided by 0, then that's right. Is there another? Now, I'm tempted to do what I did before and do a homomorphism. And I'd like to make it easy the way I did last time. And what the reason it was easy is I went to C mod 5, 5 divided 10, and so that made this term go missing. Squared. This isn't going to work so well for me here because my choices are 2 and 47 if I want to make this disappear.
Yeah.
But it doesn't matter because I know that x squared equals 1 bar will have a solution, namely 1. But it's not like the previous one where I said, okay, there's no solutions I've done. What do you think? This has infinite many. Smallest is x is 14395. Y is 221,000. It's not obvious, right?
Yes.
Not obvious at all. And in fact, there's infinitely many of them, and that's the smallest. So the point of this is these equations can sometimes be a little tricky. Okay, questions? Okay, so we've already got the first isomorphism theorem under our belt. I'd very much like to one of the groups said that extra ring structure to it. Here comes the second one. Second isomorphism theorem. Oh, and by the way, you all and people out there in Etherland too, before I eventually erase this, don't forget our next exam is on Friday, so our review session will be next day of class, Wednesday at 5 o'clock. He's not here, but just across the hall, mark 301. Okay. A and R, the subplane, and B, ideal. Then A plus B remember, B an ideal, that means a subring on steroids. So this is a subring that's got some extra vacuum from their power. What is A plus B? This is, I think, very suggestive notation. It's just everything like this. It can be written as form something in A, something in B. It's a subring of R. And A intercept B is an ideal of A. So when you intersect the ideal of R with A, you get an ideal inside of A. Notice this setup is almost exactly like the second isomorphism theorem for groups. And finally, this is isomorphic to A. Notice this is exactly the same statement as the second isomorphism theorem for groups. The only difference is we write this notation additively. So let's go through some of the details of this. A plus B okay, if I only think of this in terms of group theory, A plus B is a subgroup of R as a group, right? Because A and B, when we're talking about R's group structure, it's abelian, so these are both normal subgroups in that sense. And remember, this is the analog of A times B. All we need is one of these to be normal. In fact, even less than that to be a subgroup. So are we good with that? All we need to do is show that it's closed under multiplication, all right? So what happens when I take and I do commuted group theory, so I'm gonna be careful here and make sure I get this right. What do I get? I get a mess. I get A prime plus B prime
Prime
plus A prime plus B. Everybody okay?
Yep.
But is this still an A plus B? Is it in the form Bill plus Fred, where Bill is an A and Fred is an B? Doesn't look right if I got too many terms. Well, I think we can all agree with this is okay. Everybody agree with that? And I will go ahead and do the spoiler. That is in B, but why?
Well, B is an ideal.
B is an ideal, so it sucks from both sides, right? When I say ideal, it's two sides. A times B prime, that's sucked into B. B times A prime, that's sucked into B, and this is sucking in both directions, but this is in B, so this is something in A. Okay, good. So this is a subring. That's the first claim. Note also,
Professor Kuykendall,
yes,
your video is not working on the Zoom.
I would love to talk to people about that. All right, folks. folks, for those of you out there, I'm gonna jump off and I'm gonna log back in, see if that works. Thanks for letting me know, Henry. See if you moving. All right. Well, hopefully that glitch is done. We will see. And there's Henry again. Henry, if that happens again, be sure and holler at me, okay?
All right, will do.
All right, so this is a separate thing. All right, good for that? Actually, I need it for it to be an ideal. So. X. Well, what do I know? I know that AX is in A. Well, actually, I'm gonna do this. X and A are both an A, so they're both an A subring, so the product is in there, no problem there. And because X is in B and A is in A, it's in A and R. So XA, AX, B. This is because B is in A. So that takes care of these two statements here. Now, to finish this off, I'm going to do the old business with, yeah. I'm going to put this right here. Okay. So let's define F let's define the function F from A to A plus B on B. Okay, so I need to have something plus B because this is going to be some coset, all right? And again, math class, right? So this is A. Or if I was to be more dramatic, I might write A plus 0. Because typical of this is like something in A, something in B, but I can just stress this in. Right? Okay. So this is. So this is a homomorphism actively. Really, I didn't have to do that because we've already done this for groups. Let me check the other one though. That's probably a good idea. But I know that this is A. Because that's how we do our multiplication. Switch rate. This is F. A, F. Next, I claim well, so We actually showed this before in groups. But it's easy to verify as well. And I'm also going to piggyback off the groups from last thing. The kernel of F is a percent. We've already shown that this is zero. Therefore, by the first isomorphism theorem, a kernel of the homomorphism is isomorphic unit, which is. Any questions on that? Okay, so I'm going to go through a little bit more detail. Probably this one, the third isomorphism theorem, round it out. Third isomorphism. And again, this bears. Okay, it looks like it's quit again, hasn't it, Henry?
No, it seems to be working for me.
Oh, maybe I just can't see myself. Okay, good. As long as it's working, you guys. Let IJ be ideals. Without contained J. Then J mod I is an ideal of R mod I. Okay, it's kind of the first big sort of breakthrough here. And we get this quotient form that we had before. This is a ring. This is an ideal in the ring. So you did this quotient, this is isomorphic. J. What is more, there's a one-to-one correspondence between the ideals. There exists a one-to-one correspondence between ideals, respectively, submarines, of Armada and ideals, respectively, submarines. Are that okay? So let's go through some of these details. I'm gonna appeal to the groups in a couple of appropriate places. I'm gonna appeal to the groups in a couple of places I think is appropriate. You know, R on I, J on I isomorphism. As groups. You know that from our passport, so, let's see if we can show this is true. The only thing that you need is the multiplicative part, so that's not too bad. I'm gonna focus on correspondence business here. So let's let T be a subring of R. Let T normalize the subring. Some subring. Now, first and foremost, this means that T is a subgroup, right? T must be in that form because we already know the correspondence to groups. It has to be in the form A mod I. For some subgroup A of R containing I. Remember, the third isomorphism for groups gives us correspondence between normal subgroups. But here, talking about subgroups in this context, they're all normal. And so whatever the subring is a subgroup, that's a normal subgroup. So it has to be of this form, where A is some subgroup part. Okay. Since T subring, then for all X, Y, and A, X plus I times Y plus I, which equals X, Y plus I, is in T. So if this is in A plus I, then that XY thing has to be in A. And so what we're essentially showing is A is a subgroup. Subring of R. Now, let me take this a step further. What if T is a little stronger? So we'll say additionally. Yeah. Yes. Deal. So now, not just a subgroup, not just a subring. Let's suppose that T is in fact an ideal. Then for all R plus I, or I, then, R plus I times T is contained actually and on both sides of the spectrum. Because it's both right and left.
Yep.
So in particular, what this means is that and so, RA must be an A for because that has to be an A. And in a similar fashion, A plus I, times R plus I, AR. And again, AR and RA must be an A. So actually, A is an ideal containing I. So in other words, if T is vacuum cleaner than A, that A part has to be vacuum cleaner. On the other hand, let's suppose that A is a subring of R containing I. Suppose A and R. Suppose that A is a subring of R. Since I is A mod I is a subring of R mod I. And because the A's are closed under addition and multiplication, and that will go through to the A mod I as well. And if additionally, ideal of R, then A mod I is an ideal of R. If A sucks everything in, then A mod I sucks everything in out of all. And that's essentially all we need there, because the correspondence, the one-to-oneness of these kind of things was shown in the group theory. And what we've shown is, if A mod I is a subring of R mod I, then A is a subring. If this is an ideal, then A is an ideal, and vice versa. Okay. Any questions? One of the things that's kind of cool, I mean, sort of from my perspective, about rings, not only give a binary operation, but you also get different ideal types that are So ideals are like normal subgroups, right? But you've got even more descriptors here. Let me start off. I am going to focus as we go on. I'm going to focus more and more on brings me community identity, but I'll try to be as clear as I can when I expect that not. Proposition. Let's let R be a community bring of identity. Okay, new notation. Commutative bring with one. That's what I mean, because those commutative and with one will be very popular adjectives to give to my ring. In I R a non-empty subset. Let's suppose that I is a non-empty subset is an ideal. R if and only for all x, y, and I and R x plus R y is enough. This is, I hope you will find this reminiscent to the subgroup criteria. This is essentially what this is. This is a subgroup criteria for ideals. If you like. Let me go through a quick proof of this. It will be kind of fun, I think, seeing where you're at. Use our hypothesis. Suppose first that I assume. And we were supposed to x and y are ideal and R is not. Right? Then RY is in I because ideals sucks that R right in to the ideal. And so that was easy, right? So if it's an ideal, then something of the formation is always not a problem. Again, this is the fun thing. Why is this enough? Well, let's feel. Here's where you use the fact that I is not empty. Just the fact that there are two things in R, not necessarily distinct, because it's quite the same. But I certainly have X, Y, and R. Note that
Wait, so X and Y being I,
that should be enough. Take R -1. By the way, this is commutative group one, so I know that one's in there. So therefore, -1 has to be in there. Notice -1 and 1 may not be distinct, but for some reason -1 is. Yes. X minus Y. So here I've used the subgroup pattern. X and Y are in there, X minus Y is in there, so I is so, right? Now all I gotta do is show that it sucks. So see then RZ or zero plus origin. So. Right, because of the fact that, you know, the silver zero is now on the dot, so this is perfectly legal move on that part. Okay, questions? Okay, so here's a proposition I'm gonna give you, which sort of also doubles as a definition, because I'm gonna use the proposition to sort of define some important types of ideals we might want to look at. Proposition. Let's let I and J be ideals, following are ideals. Following are also. Number one, I intersects J. Notice where you point out on one, you already know that's a sum, right? So all you have to do is show this as vacuum cleaner property. Number two, I times J. Now, let's be very careful about what I mean by this. I define this in the homomorphism. This is a set of things like this. Finite sums. So it's not just, be careful about this, it's not just a single element of I times a single element of J. Because I don't expect that subset, that'll be closed under, it won't even be closed under sums. But I don't expect alpha one plus beta one plus alpha two plus beta two. I'm sorry, alpha one times beta one plus alpha two times beta two. I don't expect to be able to write that again as a single alpha times beta. So you do.
Is that K at the bottom of the sum supposed to be an I?
Yes, it is. Thank you. And I guess that means you can read the board, so that's or somewhat. I'm going to do this from first for the matter. I plus J is expressed in each fraction. We've already shown, well, there's no need for sums here because you can regroup these sums. We've already showed that this works, this one. And I squared would be taking J to be I. And then this goes by induction here. This is probably not too surprising. This is the set of sums. I, 1 to n alpha F1. 1 comma I alpha 2 comma alpha no alpha or alpha I J I. So it's just an inductive extension of let me make a couple of remarks. One, I plus J is the smallest ideal of R containing both I and J. So this is the smallest idea that you can make these both of these, it's all sums of it. And also, IJ is always contained in the intersection of I and J. So, for example, let me kind of point this out here. So let's look at these. Example here. Let's go through it. What's the intersection of these two?
Z.
36?
I believe so.
Yeah, so 36 is in 12Z, 36 is in 18Z, all right? That sounds right. What is the relationship between 36, 12, and 18? Can't you at least answer that question?
36 is the least common divisor.
That's right. I think we can all agree that this ideal is contained in both of these, right? Because 36 is 3 times that, and 36 is 2 times that, so it's in. And it's pretty easy to see that they can't be more. How about the product? I think this is what you might think it is. Hey, anybody want to guess?
Would it be just 12 times 18Z?
12 times 8. Right. I think that's right there. That's right, because anything in here is in the form 12 times an integer times 18 times an integer, and then summed up. Actually, it turns out that this one can be written, everything can be written as a single. You don't have to write the sums out for this particular example. That's actually rare. How about the sum?
Is it 30Z?
That one a little weird. Let me ask you this. What's the relation between 12, 18, and 6?
Greatest common divisor?
6 is the greatest common divisor. Let me point out, and this takes us back to our days earlier with the integers. Notice that 6 is in this ideal, right? Just take negative 12 plus 18, right? So
Oh,
this ideal
okay.
has to at least have 6 in it, right? And any linear combination of this has to be divisible by the greatest common divisor, right? And so it's got that. And I'll skip forward because it's an easy distinction of this. Any questions? Okay. Let me give you one more definition that we'll talk about next time. Let's let R be a ring and A a subset. And A and R subset. This time the subset can even be empty if you want it to be. The ideal generated by the A is the smallest. If you generated by A is the intersection of all ideals of R hanging out. And we'll talk a bit more about what this means next time. But let me ask you all this. What would the ideal generated by the empty set? Would be the intersection of all ideals that contain the empty set. But remember, every set contains the empty set, so it's the intersection of all ideals. Can anybody tell me what that is? Every ring sort of has the smallest ideal. What's that? Good, 0, right? So the ideal generated by the empty set. Okay, any questions? I will be in my office for e-learning day. Since this is e-learning day, I'm going to try to remember when I go back to turn on Zoom. So you're welcome to jump on that if you've got any questions. If I forget, please email me. You're welcome to come by or get on Zoom and take it from there.
Okay.